Alright, hello and welcome to Lab 5. This one is a very exciting one. There's a lot of code involved. You don't have to write most of it, but it is just so cool, I think, once you get it working. It is about tic-tac-toe, and we are going to model tic-tac-toe and all the ways that it could be played as a tree. So let's review what binary trees are and how they're implemented in C++. Remember, you have got your nodes. Here's an example binary tree that holds numbers. Here's your root node. If you go left, you get to some other node. Maybe that's the 13 node, I don't know. Let me draw this slightly better. And then if you go right, you can get to some other node, get to the 55 node. And eventually, you go left and right and you find nothing. Those are your leaves. This 13 would be a leaf in that case, but maybe you can go further. Maybe some of these have more nodes, this is 43. I guess this is a binary search tree now. But it all works out. And so that's an example tree, binary tree. And remember how this is all going to be implemented deep down. Every node has the data that lives inside of it, and then also pointers to the left and right children, which could be null if they are going to be leaves, or if there just is not one of the children, but one of the other ones exists. Struct node, and then you have some data, maybe an int, whatever kind of thing you're trying to store at each node, and then pointers to the left and right. Node star left and node star right. And so that is your struct node, and you make a bunch of these and you link them together. Okay? That is how you make a binary tree. We are going to go a bit further in this lab. We're going to make not binary trees, but just generic trees. So we're going to end up with more than just left/right child nodes. We're going to have a whole set of children. So it's just going to be a set of node stars of children. And that's how we'll represent them. If it's a leaf, the set will be empty. And sometimes some trees have parent pointers, the parent of 55 is 42, the parent of 13 is 42. The parent of the root would be null. There's nothing there. Some trees do that. And I guess the final thing is that we know that shared pointers are so much cooler than normal pointers, so I guess I lied when I said we're going to use a set of node stars as children. We're going to use a set of shared pointers to nodes. That's what we'll be using to represent our set of children and how we get to them. So that's binary trees, and we are going to make a tree that represents how tic-tac-toe could be played from a given point onwards. Right? So I have built an artificial intelligence engine that plays tic-tac-toe and finds the best move, which will be fun once you get everything working. Your job is to enumerate the moves and do some traversals and things like that. So it's actually not hard to make a tree of every possible game state. There's, at most, here is your tic-tac-toe board. In every spot, you can put an X, an O, or leave it blank. And so there's 3 options and 9 things. So there are at most 3 of the 9 possible game states. That's not really too much. That's fine. We can store that inside of a computer. What we will do is we're going to make a tree of game states to figure out all the ways that we could play an entire game of tic-tac-toe or a game from a given starting point. And so here's an example tree. So from the very beginning, this is the root of the game board progression tree. At the start of the game, the whole board is blank. And then let's pretend that it's always X's turn first. And so what could happen in this board after X moves? Well, X could have gone here and left the rest blank, of course. Or X could have gone here, right? Or X could have gone here. So these are all possibilities. And then, there's a million of them. And then at the very end, or X went all the way down here. There's 9 children of the root node for each place where X could go. And then we're going to start enumerating all of these subtrees, what could happen next. Now it's O's turn, of course. And so maybe here, if O makes a move, maybe they could definitely go here, and X stays there, of course. Or maybe the O goes here, or maybe the O goes here. There's so many options, right? There's a million options all the way down to O goes here, and there's options for those. So there's a ton of subtrees here. There's a ton of subtrees here. A ton of subtrees here. And now it's X's turn again on this round. There's now place X in a bunch of places. Place X in a bunch of places because now it's X's turn. And then eventually, like, you get deep down and you can find all the places where somebody won, and we'll talk about that soon. Okay, so that's an example tree. That's how you go down the tree. Like, it's X's turn first. Here are all the moves for X, and then you enumerate the subtrees for all the different ways that O could play from that point on, and now it's X's turn again, and you just keep on switching back and forth. So after we make this tree, we can search for our current game board, and we can search from there onwards, the entire subtree of all the different ways that the game could be played out from there on. We can find the spot or the best move that will minimize our opponent's chances of winning and therefore maximize our chances of winning. Isn't that cool? So it's like maybe we want to find that there's a way. We want to find the best way to get to a winning state for maybe if we're X, something like this, where O went there and went there or something. Who knows? Okay, so that is what's going to happen here. All right, and yeah, so that is the game in a nutshell. Let's kind of talk a little bit about the code that you're going to be writing. So you're going to write this function that enumerates the game board. First of all, you're going to start with an empty one and then start making children, like add the X in all the places, and then it's going to be a recursive process. And to represent each game board, we're going to represent game boards as a vector of vectors. So we're going to have, it's going to look like this. So every game board, like this winning game board, for example, we're going to represent it as blank X O, O X blank, and blank X blank, and these will all be just characters. The X character, the O character. And the way that we'll represent this in our program is a vector of these characters, really a vector of vectors. So like here's the first row, we put that into a vector. Here's the second row, we put that into a vector. Here is the third row, we put that into a vector. And then we make a vector of all of those rows. So that's how we're going to represent each game board. It's going to be a vector of vectors of characters. And that's how we'll represent that particular game board, where dash means blank, and X's and O's, of course, mean what you would expect, and you want to think about it like this. So that's how we'll be representing our boards, and with that in mind, I think it's time to look at the code. All right, we'll go and talk about the things that you'll be doing. So here are all the files you'll be living in the tic-tac-toe.stuff, tic-tac-toe.cpp, fim tic-tac-toe. Let's look at the header file at least. But like, yeah, here's what a game board is. I'll use a type def so I can just say board instead of saying this giant thing. So it's a vector of characters. That's what a game board looks like. It holds the game board like this. And let's see, for every node in our game tree, right, we have every node in our game tree. This is a way to compare shared pointers that's useful for sets. But every node in our game tree holds the current board. That's our data. So it's like, here is the board, and we encode it like this, of course, and then we hold all the children of each tree. So imagine like we're at the root where everything's blank. We hold an empty board, blank board, and then we have a set of shared pointers to game tree nodes. Those are our children. It's more of us, more nodes, but we're going to have a set of them. And because this is a custom class game tree node, we have to give a comparison function. Here it is right here, to actually be able to put it into a set. Otherwise, it doesn't know how to order things. And so those are our next moves. These are our children. All right. So every game tree node holds the current board state and then a set of children, and each child is the next move that could potentially be made. And you know that you're at a leaf if the next move set is empty. That means you have no children. All right, if the set is empty. That's the idea. And then we have this big giant class that represents an entire game tree. Of course, we represent it as a pointer to its root. That's what we hold. And then we're going to build it, of course. We're going to build the tree, given a starting point and like whose turn it is. And I'm going to have you implement a few of these. I've solved for the best moves. I'm going to have you implement the breadth first search. There's a lot going on there, but a few of these you'll be implementing, and it's all, though, in the tic-tac-toe.cpp file. I've done a lot of it. There are only a few fix-me's. So here's like my comparison function and all that. Here's the constructor for a game tree. We start out the board empty, and then we're going to make our root of the game tree as a game tree node. We're going to make a brand new game tree node on the heap and set the board to be the empty board, of course, all dashes. and set the root of ourselves. And then finally, we're going to build a tree recursively, starting there, and it's X's turn to move next. All right, so you are going to be implementing this build tree function, and that is going to be the bulk of your job. All right, this will be hopefully the fix me's make it self-explanatory, but it is a recursive function. It's a recursive method, I guess, that builds a tree starting at a certain node, and it just enumerates all the potential moves from there onwards, given that the player is the one who's moving right now. It's going to either be X or O. And so let's talk about build tree. So you are going to be given a current game state, like maybe it's the empty game state, maybe it's this game state right here. So you're going to be given a pointer to the current board that you're working on, the current game tree node that you're working on. You're trying to fill in its children, and then you're also going to be given whose move it is. Whose move it is. So, for example, you're going to be given a subtree root, and let's say that points to this node. Maybe it has X, O, OX, that's the game board, and right now the children are empty. There are no children at all, but it's your job to fill them in. And so this is your subtree root. It's this game board node, and then you're also given whose turn it is. If X goes first, that means it must be X's turn right here. So the player will probably be X for this example, and then your job is to figure out all of the immediate next moves. So, for example, you have to build all these nodes. You have to build a node for, all right, take your current board and then add, like, X could go here maybe. X, X, O, O, maybe X goes here. You have to build another board where maybe it looked like this, X, O, X, O. Maybe X went, I guess I could go here. Let me do it in order so it makes more sense. You're probably going to want to go top down. So let's swap those. So like X could have gone here, or X could have gone here, and you're going to enumerate every possibility. You're going to build these nodes, and then you're going to recursively build their subtrees out. See that? That's the goal. Figure out your immediate next moves, put those as children of your subtree root, and then recursively build the tree from there, from your children onwards. All right? That's the goal. And it's a smaller subtree now. Like, this is a smaller subtree to build, so it's recursive. You can use induction to prove that it's going to work out. And eventually, you're going to hit leaves, where either the board is completely filled, there's nothing left, or the game is over, and those will be your base cases. You don't put any children underneath this board because no more moves should be made. There's a winner. Or if the board is full, of course, you can't, like, overwrite anything. So those are going to be your base cases. But I hope that build tree makes a little bit of sense now. And so what you'll do is you will get all the next boards that could be made from the current board stored inside of here. And I've made a little helper method for you to do that. Here's generate next moves. So given a current board and whose turn it is, it gives you back a set of all the different moves that the player could make. So you're welcome. Did that for you already. You'll just call that. Here's all the next possible moves, and then you need to turn those into game tree nodes, right, on the heap. So this is you building up a set of next moves, and you're eventually going to put that inside of your subtree root, all right? That's the goal. And so yeah, for each next move that you can make for each board, you're going to make a shared pointer to a game tree node on the heap. For that particular child, you're going to make this node, and then set its board to be this board that you just made, and then recursively build the tree out from there onwards. Remembering that, like, when it's a child of this board, now it's O's turn. You have to swap the player. Like, if this was X in your children, the player is now O. If this was O in your children, the player is now X. And then you'll add this child into your next move set, and eventually this set, it's just a local variable. You're going to put it into the subtree root. Like, you're just building all these separately, and then you're going to attach them to this guy with all of those links. You'll add them. You'll just set your next moves into the subtree root at that point. So that's the recursive function that will enumerate every possible play of the tic-tac-toe game. I hope that makes a little bit of sense. It is recursive, so it might be a little hard to wrap your mind around, but hopefully the fix-me's help, and please yell at me if you have any questions about that stuff. So that's the first thing that I'll be writing. Another function, or method really, that you'll be writing is the winner method. And this will take a game board and it will tell you if there was a winner or not. And so scroll down to that. It's a simple function. It takes a board and it returns a character representing who the winner is. So if the winner is X, say it's X. If the winner is O, say it's O. If there is no winner or it's a tie, say question mark. All right, so that's what my helper functions are going to look for. So for example, to generate the next moves, it'll make sure like I'm not going to make any moves if somebody won, something like that. So yeah, you'll implement this winner function, which takes a board. Maybe it looks like this, and you'll be like, oh, the winner's X, so you'll return the X character. Or if the board looks like this, like not enough people have moved, or it's inconclusive, you'll return question mark to mean that there is no winner, okay? And so it's your job to check for a winner. You have to check every possible way, right, to win in tic-tac-toe, like either you won the row, or a column, or a diagonal. You have to check all of those possibilities. There can only be one winner, though. All right, so see who the winner is and return that character. So it's going to be a bunch of if statements. All right, so that's the winner method. And then finally, the last thing that you need to implement is the BFS function. So I want you, or I guess it's always a method still, it's part of game tree, but I think of it as a function. It's just like a little helper. And so this is going to perform a breadth-first search of every game tree node, all right, starting at the root node. So technically, this is just for fun. It's just to give you practice with breadth-first search and traversals and things. But yeah, I'm going to make you do it anyway. And this needs to search through the entire game tree and visit every game board in breadth-first order. So you're going to build up a list of all the boards that you see. And so add them in order to this list, and I'll return that. Okay? So traverse, and every time you see a new node, add it to this result list. And so remember what a BFS does. It's going to involve a queue, and the order that you should get things back out is, let's make this a very generic looking tree. It's going to go in, remember it's this order. Whee! So the nodes that appear, the boards that appear in your list are going to be in order like this is the first one, this is the second one, third one. This should get pushed fourth, fifth, sixth, seventh, and onwards. Okay, so that's breadth first. And so you're going to go through the board that you built up. It's your member variable. It's the root. You're going to start at the root, and you will go and traverse in a breadth first fashion every time you visit a node, add its current board to this list in order. Just keep pushing it back. And so that will let them all appear in level order, and that's that. Okay, so that is BFS. That's more or less your lab. Let's see if there's anything left in the write-up. This will be due week 16, by the way. So we got the code. I've talked a little bit more about stuff here, so feel free to read this if you'd like. But yeah, your job is build tree, winner, and BFS. Okay. Compile as usual, run the tests. I guess I should show you the tests. And so here is the test function, all the test functions. Let's see here. If you run it like this, if you say /tic-tac-toe run test, it will run my tests. Otherwise, it will do something cool that I'll show you in a second. But like this one just tests that your winner method is working, has some boards. This one tests that the build tree is doing the right thing. It's making sure that like, here's the starting board. It's making sure that you should be producing these boards as the children of that board. Things like that. And then the children of those, Just checking that. And then it's also testing BFS. And the way that it's testing BFS is here is a reference file. And here's a single board printed out just in order, just as a line. And so this is like the empty board. This is the X in the very last position. And so these are all the boards that we should see in order in your BFS output. They've just been squished to a single line. And so these are all the boards that we should see in that order. There should be 549,946 of them, apparently, added output into that list. So that is the reference file that I'll be checking you against. And so let's go back to the tests. Oh, yes, that's more or less it, what's going on. I have some simpler tests as well, just making sure that all the correct things are in there. So yeah, that's that. And kind of the coolest thing is once you get all this working, it will hook into my code. I've made this artificial intelligence algorithm. It's called Minimax. I can tell you more about it if you would like to in office hours. But what it does is if you run test tic-tac-toe by itself, it will let you enter a game board and whose turn it is. Like you can enter this board in just a straight line like this, and then say it's X's turn, and it's going to search for the next best move according to the Minimax definition of best. And I can, of course, tell you more about that, but it's going to run one of my little methods here. It's going to use the tree that you built, of course, and so it like computes a score for each possible move, and it tries to return the biggest score and find the best next move, the one with the highest scoring outcome, the one that's going to end up with the most wins, essentially. And so yeah, that's the best next moves method that will be called for you and using my code. But yeah, that's just a fun reward after you finish all this. You don't have to care if you don't want to, I guess, but it is in there for fun. And remember, though, that X will always go first in our model of the game. So that's why in the constructor, we're building the tree starting at the empty board. That's our root, and then it's X's turn to move. Okay, so that's that. That is game tree. That's everything. I'm not having you implement any tests. I'm just having you implement those 3 methods of the tic-tac-toe.cpp file, and that is all. So please get, what were they? Build tree and winner and BFS working. I think build tree will of course be the hardest one, but please follow the fix me's. It should make sense. And that's that. Turn this in and yell at me if you have any questions. So that is your lab 5, and it will be due in 2 weeks. So yeah, I think that is all that I wanted to say. Good luck, and yell at me if you have any questions.